Oh, there we go. Yeah, I think we can wait 5 more minutes, right, as usual.
What's interesting is no one's here on Zoom and no one's here.
Right? Yeah.
Do the link because Melina found us. And Emily found us.
And the only people on Zoom are people here.
Sure.
Yeah. So the organizer and limiting your capable. We will wait.
Oh, yeah, council takes a long time to boil.
Your kettle or on a stove?
Yes. There's no stove next door.
Mm.
I mean, I suppose you can microwave the water, but that is considered anathema.
No, it is my coffee.
I mean, with coffee, I'm not gonna.
Oh, yeah. There we go.
Some people do have standards for coffee, but I personally don't, so it's okay.
It's not about the coffee, it's just the caffeine.
Caffeine in it.
I mean, is it instant coffee as well?
It is instant coffee, yes, of course.
That is gross. I used to drink that.
We quickly went from it's just the caffeine to it's gross. Like, very good. No, it's understandable. It's just like the caffeine. It's instant coffee. It's just terrible.
Yes, but keep me away.
Yeah, no, I'm 100% on your side. I'm just saying we went from no, I understand you, of course there is. Where's the rest of our group?
It's the vodka group.
Yeah.
There.
Chayoni.
All right, so I don't know. I don't see her that often.
And
We should probably.
right? Yeah. Yeah, thanks everyone for coming to this third fraction. I'm trying a new word every installment of this thing. Let's see how it's gonna play out. Today, thanks Emily for accepting this invitation. Today we have Emily Adlam. She is, I'm always cheating. She's an assistant professor here at Schmidt College of Science Technology. Is that correct? At Schmidt Science?
Yes,
Yeah, okay. Schmidt College of Science and Technology. Yeah, she did. Again, yeah, she did her PhD in Cambridge under supervision of Adrian Kent, and then a postdoc or 2 postdoctoral position in Canada, 1 postdoc in Canada, and we are happy to have her here now with us at Chapman. So, and today she's going to talk about what black holes teach us about Wigner's friend. Floor is all yours. You know the drill. So, thank you again.
Great. Thank you everyone for coming and thank you for the invitation. This is partly linked to our Templeton project, this talk. So I thought I would talk about our quantum agency focus and specifically some things I've been thinking about recently with respect to Wigner's friend. This is very much a work in progress talk. I'm still thinking about all these things. I'm hoping you're all going to give me some new ideas and insights that will help with some of my puzzles about these things. So a lot of this talk is going to be based on thinking about a recent paper by Hausman and Renner that you may have read, where they argue that the Wigner's friend paradoxes are in fact just the same as the black hole firewall paradoxes. I really like this paper. I think they're totally right in pointing out that there are important connections here. But in this paper, they don't say much about like what the connections mean or what we should conclude from this. They just kind of point out the connections. So I'm sort of making some attempts here to try to understand if we grant that there are meaningful connections between these cases, what does that tell us about the Wigner's friend paradoxes and how we should think about them? So I'm going to start with a short survey of Wigner's friend paradoxes. I'm not going to make any attempt to be unbiased here. I'm going to present the way that I find most perspicuous for thinking about these things. Then I'll present the two Wigner's friend paradoxes that Hausman and Renner focus on. Then I'll present the two black hole paradoxes that they're comparing to. I'll say something about the connections between these things. If there's time at the end, I'll talk briefly about another thing I'm working on also related to Wigner's friend. Okay. So the Wigner's friend paradox, as we all know, Alice performs a measurement in the basis 0, 1 on a two-dimensional system S, originally prepared in the state A0 plus B1. Alice presumably sees some outcome. Suppose she sees outcome 0, then presumably the state of S should be 0, the eigenstate corresponding to the outcome. But if Bob watches from the outside and describes all of this using unitary quantum mechanics, then it looks like S and Alice should be in the entangled state shown here. Obviously, one way to avoid the paradox we've seen we arrive at here is to just say that quantum mechanics is wrong. There's some kind of collapse of the wave function when Alice sees her outcome, and so Bob won't actually see this entangled state. But I'm not sure that the black hole paradoxes have much to tell us about that kind of approach. So here I'll focus on approaches which are seeking to maintain what I call first-person universality. So the idea that quantum mechanics, as applied by any individual observer, is right for measurements performed by that observer. So from a first-person sense, quantum mechanics will always turn out to be right. So if we want to maintain first-person universality, we have to say that in this situation, the eigenstate 0 is the state which is going to correctly predict Alice's next measurement on the state S. But meanwhile, the state which correctly predicts Bob's measurement on that state S is going to be the trace of the entangled state shown here, tracing out Alice. And of course, those are not the same state. So what we see here is that if we really want to maintain first-person universality, it is necessarily the case that quantum states have to be relativized in at least a sort of effective empirical sense. So specifically, the quantum state that correctly predicts the results of one observer's measurements on a system S at a given time t is not always the same as the quantum state that correctly predicts the results of another observer's measurements on that same system S at the very same time t. So this is quite a mild and non-radical sense of relativization. All we're really saying here is that Alice's measurements are a different set of physical events to Bob's measurements. They might have different features, they might produce different results, and so it could sometimes be sensible to describe them using different states. So relativization in this mild and not very radical sense is there even in Everett and de Broglie-Bohm. Both of them use relative states in various settings for various applications, even though they do also have a sort of absolute description going on underneath. Great. So if we want to maintain first-person universality, Wigner's friend is pointing us clearly towards some kind of relativization. There has been a lot of interest recently in approaches which are more radically relational than Everett and de Broglie-Bohm. And there's two different axes along which a view could be more relational than Everett and de Broglie-Bohm. One is that it could be inherently relational. So it could say that quantum states are by their very nature descriptions of a system's dynamics relative to an observer or to some other system. And in that case, it simply doesn't make sense to postulate an underlying absolute quantum state. That's more relational than Everett and de Broglie-Bohm because both of them do postulate an underlying absolute quantum state, which is not relativized to anything.
Emily, can I ask you to clarify on the sense in which a state is a representation of dynamics in the first option?
In the sense that the state predicts the outcomes for certain kinds of dynamical interactions that could take place.
Measurements you mean?
Yes. Yeah. And yeah, so that's one way in which it could be more relational is to say that states are only descriptions of dynamics relative to an observer and they can't be postulated in an observer independent way. The other possibility is to go to a kind of fact-based relationalism where we are relativizing not just the sort of the dynamics and the predictions, but the facts in some sense. I'm still not convinced that's a coherent possibility, but let's allow that for the moment. So that leads to views such as sort of relational quantum mechanics and various sort of Copenhagen-ish views. So we see that we get a kind of four-way taxonomy of different types of relational views that we could adopt in response to the Wigner's friend scenarios. And the reason I'm presenting this is because I think that the original Wigner's friend paradoxes and extended Wigner's friend paradoxes don't really clearly differentiate between these four options. All of these will kind of work as resolutions to most of the original extended Wigner's friend paradoxes. But what I'm going to argue is that I think maybe the black hole versions do push us more towards certain categories here than others. Okay, so that was the original Wigner's friend paradoxes. Recently, there's been a little cottage industry trying to come up with various extended Wigner's friend paradoxes, which essentially extend the Wigner's friend situation to more complex scenarios and use that to try to derive various kinds of contradictions. So I think it's helpful to divide these paradoxes into two different classes. The third-person universality ones are the ones where the paradox relies on the assumption that quantum mechanics is going to produce correct joint predictions for any pair of measurement outcomes on a space-like slice, even if nobody can see both of those outcomes or ever compare them. So it requires a sort of third-person sense of correctness of quantum mechanics. And so that includes most of the Wigner's friend paradoxes, including the Frau-Sugar-Renner paradox, the League-Water paradox, and the Ormrod and Barrett paradox. There's also a set of paradoxes which use first-person universality, so that's where the derivation of the paradox relies only on the assumption that quantum mechanics, as applied by each individual user, will produce correct predictions for measurements made by that user. So that includes primarily the Bong et al. Local friendliness paradox. So in this paper, Hausman and Renner use only third-person paradoxes as examples. I think that's maybe a bit of a weakness of the paper because I do think that the first-person paradox is in some ways more interesting. And I'm going to argue later that actually I think the black hole paradoxes are perhaps more analogous to the first-person paradox than to the third-person examples that they use. Okay. With that in mind, I'm going to present the two paradoxes that they describe in this paper. So the first is a case where we imagine Alice performing a measurement on a quantum system in the diagonal basis. Then Bob reverses Alice's measurement procedure, erasing her outcome presumably, and then he performs a measurement on the same system in the computational basis. So this is supposedly a paradox because Alice and Bob have been able to measure a single system in two incompatible bases. That seems like it should be impossible given standard quantum mechanics. Now, the reason this doesn't lead to any outright contradiction is because Alice's measurement gets erased by Bob, and that means that no individual person is ever going to see anything which contradicts quantum mechanics. These two measurements are not jointly accessible to anyone. And that's kind of a through line which is going to run through all four of the paradoxes they discuss. All four of these paradoxes, the resolution seems in some way to hang on the fact that there are certain pairs of outcomes that nobody can compare to each other. That means that we can easily solve this problem by adopting any relational approach which denies third-person universality. As long as we insist only on first-person universality, we can happily say Bob's results here conform to quantum mechanics, so do Alice's. We can't compare them because there's no situation in which these results can be compared, so quantum mechanics just doesn't predict anything for them. So that provides a straightforward way of resolving this kind of paradox. The next paradox that we're going to consider is what I'll call the second Wigner's friend paradox. This is essentially a version of the Frau-Sugar-Renner paradox, simplified and altered a little bit to fit the case. So in this case, we have Alice and Charlie in their individual laboratories performing computational basis measurements on a pair of entangled qubits, QA and QC, inside their respective closed laboratories. Bob is then going to reverse Alice's measurement and perform a diagonal basis measurement on the qubit QA. Darwin, meanwhile, reverses Charlie's outcome and prepares to measure the qubit QC in some basis. Now the thought is that by looking at his outcome and making some assumptions about what Alice and Charlie must have seen if quantum mechanics is universally correct, Bob should be able to predict with certainty the outcome of a computational basis measurement performed by Darwin on QC. He does that by looking at his outcome, making some assumptions about what Charlie should have seen because Charlie's entangled with him, using that to make some assumptions about what Alice must have seen because Alice is entangled with Charlie, and then using that to make assumptions about what Darwin is going to have to see because Darwin is entangled with Alice. It's kind of like a sort of step-by-step process from one person to the other. So that way he gets a prediction in the computational basis. But also by applying quantum mechanics directly to everyone together and just doing unitary evolution, he can predict with certainty the outcome of a diagonal basis by Darwin on QC. So it looks like he can predict with certainty the outcomes of two incompatible measurements on the same qubit. Again, seems like a contradiction with standard quantum mechanics. So again, the resolution of this paradox is going to hinge on the fact that there are certain pairs of measurements here which nobody can directly look at. So Bob is assuming some things about what Alice and Charlie's measurements must be given his own outcomes, but he can't actually go and check that. Those measurements are erased. Nobody can see what those measurements actually produced. And so to make those inferences, Bob has to appeal to some kind of universality principle. Hausman and Renner use what they call the consistency of knowledge to do this. And this is just the idea that if Bob knows that some other agent has correctly arrived at some quantum description, and this description predicts that a certain measurement will have a certain outcome, then Bob should take on that prediction as his own. And this is, of course, close to what I have called third-person universality. The reasoning here requires Bob to make some observations, assume that the result of another measurement that he can't possibly go and see must conform to the quantum predictions in accordance with his outcome in a third-person way. So obviously one way to resolve this paradox is just to deny third-person universality and go to first-person universality. Then we can say every individual person in this case is going to see things that are consistent with quantum mechanics, but we don't have predictions across pairs of measurements like this if they can't be compared. Now, Hausman and Renner don't like that as a solution because they worry that if we reject what they've called consistency of knowledge, that is going to prevent us from sort of doing science in the ordinary way. They worry that it means that we can't listen to each other and rely on one another's reasoning. I don't think that's right. I think primarily what happens if we deny consistency of knowledge is that we are saying that the predictions for the outcomes of a measurement performed by, say, Charlie don't necessarily have to be the same as the predictions of that same measurement performed by Bob, because those are two different measurements performed by two different people. It can be the case that they just have different outcomes because they're under different circumstances. And in this situation, it's still possible for Bob to understand Charlie's reasoning and to agree that Charlie has made the right prediction for Charlie's measurements. Bob just needs to keep in mind that the predictions for Charlie's measurements are not always going to be the same as the predictions for Bob's measurements. So I don't necessarily think that denying consistency of knowledge is as big of a problem as they seem to think it is. Great. So those are the two Wigner's friend paradoxes that they're discussing. And what we see is that both of those paradoxes can quite straightforwardly be resolved if we just sort of deny the expectation of third-person universality for quantum mechanics. So now moving to the black hole paradoxes they're discussing. The first black hole paradox that they present is supposed to be compared with the first Wigner's friend paradox. So their idea is that we'll have Alice carrying a qubit into a black hole which is older than the page time. Once inside, she's going to perform a measurement in the computational basis on it. Meanwhile, on the outside, Bob is going to collect all of the Hawking radiation that this black hole has ever produced, and then eventually, a standard quantum field theoretic calculation tells us he should be able to reconstruct this qubit Q. So Bob then measures Q in the diagonal basis. So now the qubit Q has been measured in two incompatible bases. That should be impossible according to standard quantum mechanics. So we can see why you might think there are some similarities between these paradoxes. In both cases, the paradox is that the same qubit gets measured in two incompatible bases. And in both cases, the reason we avoid sort of outright empirical contradiction is because it seems as though no individual observer can ever know both of those outcomes at once. In the Wigner's friend case, it's because when one of them gets erased. In the black hole case, it's because presumably once Alice has gone inside the black hole, it's going to be very difficult for Bob to then access her outcome. So that suggests that both of these approaches can be resolved by just rejecting third-person universality, adopting some kind of relational approach and saying, Alice, each person individually will see things that are consistent with quantum mechanics, but that there's no need for there to be a joint global description. And that way of thinking about the paradox is very similar to the sort of black hole complementarity idea. And so we sort of see some connections here between black hole complementarity and more general relational approaches in quantum foundations. With that said, there are, I think, some important differences between the paradoxes. In particular, the mechanisms which prevent joint access of the outcomes are quite different in these two cases, and we can perhaps learn something from comparing them. So in paradox 1, Wigner's friend, it seems natural to think that the reason the reason this outcome becomes inaccessible and the reason why Bob can then do another measurement is because there's some physical disturbance. Bob actually reverses Alice's measurement and thus kind of scrambles the information it carries in some kind of local physical interaction. So as Aronson puts it, it's hard to think when someone had your brain. Seems to be something kind of quite violent going on here that destroys this information and allows Bob to make a different measurement instead. Paradox 2 at BH is quite different from this. In this case, Bob doesn't act directly on Alice or on the black hole. So what's going on is not just a simple sort of physical scrambling effect. It doesn't seem that Bob is literally destroying this information. Now, there are some forms of complementarity which want to suggest that the inside of a black hole is in fact literally identical to the state outside of the black hole. So if you adopt that kind of approach, maybe you do want to say that in some sense Bob is acting directly on Alice. But certainly there's still some kind of radical non-locality going on here. It's not as simple as Bob just directly interacting with Alice and scrambling her information.
Do you mean one BH there?
Yes, I do, yeah. Great. Furthermore, there's, in addition to this kind of spatial non-locality, there's some weird effects going on here with regard to locality and time as well. You might think, for example, that what the important moment here is the moment at which Alice crosses the event horizon. That's the moment at which her measurement outcomes are going to become inaccessible on the outside. So it seems as though something quite important happens there. But of course, the event horizon can't even be defined in a local way. The region inside the event horizon is defined as the whole of the space-time manifold minus the causal path to future null infinity. So it's just all and only those points such that you couldn't send a signal from them to some point in the infinite future. And that means that where the event horizon is located today is going to depend on what I throw in the black hole tomorrow. So there's not a sort of well-defined local temporally straightforward fact about where that event horizon is. And so we can't sort of tell a simple story where Alice just crosses some line in space-time and thus her results become inaccessible. The explanation for why no one can access both of those measurement outcomes does seem to depend in quite sensitive ways on like global and teleological facts about the structure of all of space-time. It's going to be hard to tell that story in a straightforward, temporally ordered way. Okay, so what does that tell us about the Wigner's friend paradox? What I think it indicates is that if we want these paradoxes to have similar resolutions, if we think that sort of similarities are pointing to something deep connecting them, then potentially we should be open to adopting some kind of retrocausal or teleological solution for paradox 1, Wigner's friend as well. In particular, I want to flag up here that the local friendliness paradox, the one I think is perhaps more interesting, uses no retrocausality as one of its assumptions. Rejecting the no retrocausality assumption has not been a popular response to this paradox. People have seemed to be more interested in rejecting absoluteness of observed events. But I do think comparison to the black hole case suggests that maybe we should rethink this. It seems like we need something retrocausal or teleological in the black hole case. And if we think these similarities are meaningful, that maybe tells us that some kind of retrocausal or teleological account is going to work in the Wigner's friend case as well. As an example of what that might look like, I like to use Kent's Lorentzian solution to the quantum reality problem. I don't necessarily think this is the one final correct answer, but it's a really nice example, which I think is really useful to think about, particularly in the context of the Wigner's friend paradoxes, because it does resolve all of them in a really straightforward and intuitive way. In Kent's approach, the idea is that the course of history gets selected according to the outcome of a measurement performed on the quantum state at the end of time. You don't need to think about that too literally. It's not performed by an observer or anything like that. It's just a way of modeling some kind of global atemporal collapse that selects the course of history. The important point here is that the way Kent constructs this means that events which are not recorded in the state at the end of time just fail to be realized as part of the actual course of history and don't occur at all. So in paradox 1, Wigner's friend, since the records of Alice's measurement are later erased, Kent's approach is just going to say that measurement actually doesn't happen. There is no outcome. Nothing at all happens inside that box. Similarly, in paradox 1, black hole, since the records of Alice's measurement are trapped inside the black hole and presumably vanish when the black hole evaporates, Kent's approach again is going to say something like, the measurement doesn't occur at all. It has no outcome. So whether or not you think that's the right solution, I do think this is a nice demonstration of the way in which we can kind of unify these two paradoxes and give an account of them, which explains them both in quite similar ways. And so that to me is perhaps an indication that this retrocausal way of thinking about them might be sort of going along the right track. Okay, this is the paradox 2BH. This is the one that is supposed to be compared to the Frauschiger-Renner style Wigner's friend case. So in this one, Alice is going to go into the black hole and distill a qubit QA, which is maximally entangled with a given qubit QR outside of the black hole. Meanwhile, on the outside, Bob collects all the Hawking radiation and distills a qubit QB, which is also maximally entangled with QR. Now we can have Bob measure QR in the diagonal basis and send a record R of his outcome into the black hole. Alice can measure her own qubit in the computational basis, and then she can receive and inspect the record of Bob's outcome. It seems then that she can use these pieces of information to predict the results of two incompatible measurements on the qubit QR, and that should be impossible according to standard quantum mechanics. Okay, so again, there are obviously some similarities here. Both of these paradoxes are designed in such a way as to lead to predicting the results of two incompatible measurements. And you might at first think that in paradox 2 black hole, we do get an outright contradiction since Alice does in fact learn Bob's outcome. But we can perhaps avoid this by denying that Bob is able to communicate effectively with Alice here and just saying she doesn't get to learn his real outcome. So Hausman and Renner therefore argue that consistency of knowledge plays a really important role in the derivation of both paradoxes here as well. Alice has to assume that what she's seen when she inspects his outcome tells her about what Bob has really seen, and then take on his reasoning as her own in order to make this prediction. That said, I'm not completely convinced that this is right, because I'm not completely convinced that we do actually need consistency of knowledge at all to formulate this paradox. The important difference between these paradoxes is that in paradox 2, Wigner's friend, Alice and Charlie never have an opportunity to communicate their outcome to Bob. Bob just has to guess what their outcomes are based on his own outcome. There's no process of communication. By contrast, in paradox 2 black hole, Bob sends a record of his outcome to Alice. And so it's not completely clear that we need to assume anything about what Bob has seen. You might naturally think that Alice can just collapse the wave function herself when she measures that record. So in particular, we might just imagine that Alice can write down some kind of quantum state description of Bob, QA, QB, QR, and the record R, evolve all of that forward, and then arrive at the prediction that relative to her, within her perspective, the record R should be maximally entangled with the qubit QR. And so it looks like we can get this violation of the predictions of quantum mechanics within Alice's perspective. And to sort of emphasize that, we can construct a different version of the perspective where we don't even use a second observer. So Raphael Bousseau suggests a different version of this paradox where we just use Alice. She collects QB outside of the black hole. She just takes QB into the black hole. Then she collects QA, and then she can measure QA and QB, and she can then make predictions for QR and two incompatible bases again. So since there's only one observer here, consistency of knowledge seems not very relevant. And therefore, you might think simply denying third-person universality and or relativizing things to observers isn't going to help here in the way that it did with the Wigner's friend paradox, because all of this seems to go wrong within Alice's single perspective. Now, Hausman and Renner criticize that approach because they note that we need to make some quite specific assumptions about the outside of the black hole in order to arrive at the prediction that R should be maximally entangled with QR relative to Alice. So specifically, we have to assume that the evolution of the black hole and all fields from the creation to the asymptotic future is a high-typical unitary, and the fields outside the stretched horizon are described by effective field theory. But of course, the asymptotic future outside of the black hole is going to be inaccessible to Alice once she's gone inside the black hole. So you might think we shouldn't use that stuff in a description relative to Alice, and so the unitary description relative to Alice is not going to predict this maximal entanglement. I think it's just not obvious what the right answer is here. A lot is going to depend on difficult questions about what is the right way to stitch together these different parts of space-time to arrive at a unitary description relative to an observer in an unusual situation, such as going into a black hole. In particular, there's a sense in which this asymptotic future is like causally relevant to Alice. We are supposed to be allowed to use it to calculate the state of a system on the outside, and such that Bob can then measure that system and communicate the outcome to Alice. And if we're allowing that kind of like causal link, it's not obvious to me why it's not permissible to use the asymptotic future directly in a unitary description relative to Alice. Certainly not obvious to me what the unitary description relative to Alice looks like if we're not allowed to do that. So there's definitely some questions about exactly how this sort of decomposition into different observers is supposed to work. So on this basis, Hausman and Renner suggest that what we're going to have to do here is adopt a somewhat stronger relational approach. So rather than just relativizing quantum states now, they want to relativize assumptions about how things evolve in the structure of space-time. So what they want to do is say assumptions A1 and A2 themselves are true only relative to an observer, and they're true only if that observer actually checks them. So they say that if Alice stays outside the black hole and performs measurements to check that the evolution is a high-typical unitary, then it will be, and then A1 and A2 are true. But if she goes inside the black hole, she can't perform that check, and so A1 and A2 don't have to be true relative to her. So this I think is a very interesting approach. It does to me highlight the need for much clearer criteria for deciding when we are going to relativize things and when we are not within these kinds of relational views. In particular, thinking about the Wigner's friend scenario, we normally assume that if Alice measures S, then Bob is going to find Alice and S to be maximally entangled. Bob doesn't have to separately perform a check to verify that Alice did the measurement. Just finding that they are entangled is the check. Whereas it seems that Hausman and Wren are proposing that in the black hole case, there is a need for a separate verification check, and they won't be entangled if we don't do the verification check. So there's some difference, presumably, between the black hole case and the Wigner's friend case that is relevant here. I'm not totally sure what the difference is supposed to be. Something to do with the interaction between quantum mechanics and space-time, perhaps. This seems like a really fruitful area to probe, perhaps, to understand how relational approaches should move forward into this context. I think for me, this is also what I would disadvantage of what I've called the fact-based relational approaches. The fact-based relational approaches have a tendency to collapse into saying everything is relative all the time. The problem with that is that if you say everything is relative, you can't then articulate useful criteria about when and how to relativize things in certain calculations. And then you sort of end up with no clear idea of how we should do these calculations, because as you can see here, what we predict in various cases changes quite a lot depending on what we do and don't relativize. So for me, that's a good reason to perhaps resist the impulse to relativize everything and instead try to have some more principled way of distinguishing between the cases where things are relativized and where they're not relativized. Okay, in any case, even if we're willing to accept this relational solution to the black hole paradox, what I want to point out is that it seems to me that relativizing the facts is not enough to solve the paradox. We are still going to need something like retrocausality. That's because we can imagine Alice preparing the qubit QB at time t1, and then later at time t2 making a decision about whether she's going to go into the black hole. So let psi be the state of QB and QR relative to Alice at the time t1. Now, the construction that we've been given tells us that if Alice stays outside and performs the verification measurements, then she is going to find that the state psi is maximally entangled. Whereas if we assume that if we go inside the black hole, it seems natural to assume that if there's no firewall, the state psi isn't going to change if she just goes inside the black hole. So it seems that the state that she finds inside the black hole should still be the same one that she's going to find on the outside, if we don't allow that the state psi depends on her later choice. That means that it seems, at least prima facie, that if psi at T1 is not allowed to depend on her later choice, then it just has to always be maximally entangled, and so she'll still find it to be maximally entangled inside the black hole, and so we won't have avoided this problem of having a violation of the monogamy of entanglement here. So if we want this relativization to work, it seems like we, in addition, need to have some kind of retrocausal effect where the state psi at T1 in some sense depends on that later choice. So again, it seems to me that if we want these paradoxes to have similar resolutions, then again, we should be willing to look into sort of retrocausal or teleological solutions to the Wigner's friend paradoxes, both the paradox to Wigner's friend and possibly also the local friendliness paradox. A further important difference between paradox to Wigner's friend and paradox to black hole is that paradox to black hole involves a violation of the monogamy of entanglement, whereas paradox to Wigner's friend does not involve such a thing. That means that paradox to black hole seems to pose a significant problem for any view which posits a universal underlying quantum state, because it looks as though this violation of monogamy is going to mean that the underlying state could not possibly be a valid quantum state. In particular, it looks as though in the sort of Everettian story, this monogamy violation is going to arise within what is naturally understood as a single branch of the wave function, since Alice and Bob are still in contact here. And if so, it looks as though there's not going to be any underlying global state which could be compatible with this, which is also a valid quantum state. So that looks like a significant problem for any approach which wants to describe this kind of scenario in a way which still posits an underlying absolute non-relativized quantum state. So to me, I think this looks like potentially good motivation for adopting an inherent relational view rather than an effective one. If quantum states are inherently relational, then there is no underlying global observer-independent quantum state, and therefore it doesn't matter that such a thing would not be a valid quantum state. So that's certainly, I think, one motivation for taking the inherent approach seriously rather than going with the effective approach. Okay, so that was more or less everything I had to say about the black holes. I want to briefly talk about this other project, which is also about Wigner's friend, trying to understand how Wigner's friend might be related to reference frames. I want to describe this because I do think these two projects are connected in some way, but I'm still trying to understand how. So if you have thoughts or feedback on that, that would be very useful. So I'm going to talk now about the paradox that I have said I think is more interesting, the first person paradox posited by Bong et al. So this is a paradox in which Alice and Chidi perform measurements on two halves of an entangled two qubit state. Bob keeps Alice's laboratory in a coherent state and performs some measurement on it in a basis which disrupts her original result and sort of erases that result. Likewise, Divya keeps Chidi in a coherent state and performs a measurement which disrupts his outcome and erases his outcome. So we have our four measurement outcomes, A, B, C, and D, obtained by these four observers. And we can show that for certain choices of measurements for these four observers, there's no possible probability distribution over these four measurement outcomes, which reproduces all of the pairwise predictions of quantum mechanics for the pairs BD, BC, AD, AC, if we assume non-locality, no retrocausality, and no superdeterminism. Now, you might at first be tempted to say we can solve this problem by rejecting third-person universality, because after all, nobody can possibly see all four of these pairs on a single run of the experiment, so what's the problem? But what Bong et al. Add here is the note that in principle we can give Bob a choice between either performing this measurement that obtains the value B or just asking Alice what her result was. And likewise, Divya can either get the result C or he can just ask Divya what her result was. And so although nobody can see all four of these results, certainly it seems that on any run of the experiments, any one of these pairs could be seen by a single observer. And so if we don't allow retrocausality and we don't allow that the probability distribution could depend on what choice Bob and Divya make about what to measure, then it looks as though we need to have a distribution which reproduces quantum mechanics for all four of the pairs. Otherwise, we're eventually going to see contradictions with quantum mechanics. So one popular response to this paradox has been the idea that we should deny absoluteness of observed events, which basically amounts to denying that there's a well-defined probability distribution over A, B, C, and D. The thought is that in some sense, there's like no fact of the matter about the relation between Alice's observation and Bob's observation, except possibly in the case where he asks her about it. So there's just no meaningful probability distribution overall altogether. I am quite skeptical about that approach because it seems to lead to severe epistemic problems. It seems to require us to say either that memory is not sort of meaningful and reliable, or that communication is not meaningful or reliable, or that like language itself is somehow not stable over time. And all of those things seem like quite dangerous for the epistemology of science. But I think there's perhaps a different way in which we can kind of respect the intuition that there's no well-defined probability distribution here without denying the absoluteness of observed events. And that comes from thinking about how this Wigner's friend paradox relates to ongoing work on quantum reference frames. So the thought here is that it seems perhaps quite natural to say that there's no fact of the matter about the orientation of Alice's axis relative to Bob's, but there is a fact of the matter about what Alice has seen. So here I'm imagining that the measurement Alice is performing is like a measurement of spin, for example. How does she do a spin measurement? Well, she does a spin measurement by comparing the spin of the particle to some axis or rod that she has in her lab, and she sees that it's either parallel or anti-parallel. Now, we'd like there to be a well-defined fact about what Alice says. We'd like there to be a well-defined fact about whether Alice has seen the spin parallel to her axis or not. But maybe we can live with the idea that at the time of Alice's measurement, her axis has no well-defined orientation relative to Bob's axis. That seems like a reasonable thing to say here, I think, because if we imagine that the theory is subject to like some kind of global rotation symmetry, that means that orientation in space-time is the kind of thing which makes sense only relative to a reference frame. So we can sort of meaningfully say that there's no orientation relative to Bob's reference frame. Whereas a fact like Alice has seen the spin parallel to her axis is certainly going to live in the invariant subspace relative to for the rotation group, and plausibly would be in the invariant subspace for other kinds of symmetry groups as well. That looks like the kind of fact that might be an absolute fact and not a relative one. That perspective, I think, perhaps suggests that there's some limitations in the way that the paradox was originally stated, and in particular in the definition of this variable A. So what exactly is A supposed to mean? One thing A could mean is that it could be the variable defined by Alice's own internal observation. It could take values -1 and 1, meaning where -1 means Alice saw down relative to her own axis, and 1 means Alice saw up relative to her axis. That's all about Alice's internal observations. Or A could be the variable AE defined within Bob's reference frame, which combines the facts about what Alice originally saw with the facts about what direction her axis is later found to point in relative to Bob's axis in the case where he talks to her and finds out. And so that one is going to also take values -1 and 1, but here -1 is going to mean something like Alice found the particle to be parallel to her axis, and then that axis was found to point in the opposite direction to Bob's axis, or alternatively, Alice found the particle to be anti-parallel to her axis, and then that axis is found to point in the same direction as Bob's axis, and then one would be defined similarly. And I'm going to assume here that the second variable AE comes to have a well-defined value only in the case where Bob performs appropriate interactions to find out about Alice's interaction. So that's the case where he talks to Alice and learns the value of A instead of measuring to find B. So I'll take it that on runs where he finds out B instead, AE just doesn't have a well-defined value because the axis never comes to have a well-defined orientation. So it seems to me that when we talk about absoluteness of observed events, what we are kind of primarily talking about are these variables AI and CI, the internal facts about what Alice and Chidi actually saw. So if we want absoluteness of observed events, we should be demanding a well-defined probability distribution across AI, B, CI, and D. But then we can't compare that to any quantum predictions, right? Because quantum mechanics is only going to make predictions for spins measured relative to some common space-time reference frame. If there's no fact of the matter about the relation between Alice's axis and Bob's axis, then we just can't really say anything about how AI and B should be related to each other. And we can, of course, compare AE, B, CE, and D to the predictions of quantum mechanics because they are all defined relative to Bob and Divya's external reference frame. But there's no well-defined probability distribution across those 4 values since we've specified that AE exists only on the runs when Bob does not obtain the value B. So if we do that, then no quantum predictions are violated. We get all the predictions we would expect, but at the same time, we still get to keep absoluteness of observed events. There is a well-defined fact of the matter about what Alice saw, and if Bob asks her about that, which presumably involves measuring her invariant subspace in some way, he will find out what that fact is. I think that suggests that possibly the standard way of sort of formulating this experiment as a sort of quantum state description maybe is missing out on some details. In particular, the standard Wigner's friend description assumes that Alice starts out in kind of a well-defined state, ready state relative to Bob, and thus transitions into this entangled state shown here. But if we say that perhaps in order for Alice to go into a coherent superposition relative to Bob, she needs to be kept isolated from Bob in such a way that she loses her alignment with him, then perhaps the correct description involves both the original quantum state and also Alice herself being in some kind of superposition relative to Bob. And then when they interact, they go into this other superposition state, which has 4 terms rather than 2. So here I've used P and A to represent states of Alice where she has observed the particle to be parallel and anti-parallel to her own axis respectively. And P prime and A prime represent states of Alice which are subjectively identical for her. They represent states where the internal configuration is the same. So again, she has observed the particle to be parallel and anti-parallel to her own axis respectively. But they are different states because they have different total orientations relative to Bob. So they feel the same for Alice, but from Bob's point of view, they're not the same state. In particular, in the case where Alice did find the particle to be parallel to her axis, the resulting state relative to Bob is the one shown here, where we have 2 different components corresponding to 2 possible orientations of Alice's whole lab relative to Bob, but we see that we have parallel for Alice in both of those components. The thought is that if Bob measures the appropriate invariant subspace, he will find out that Alice is in the state P or P prime, so he'll learn the actual result of her measurement. But if he performs quantum experiments on the orientation variable, he will see quantum interference and reproduce the usual quantum predictions. So this state allows us to both get the right quantum predictions, but also maintain absoluteness of observed events in the sense which I think is sort of epistemically relevant. Okay, so both of these projects are still work in progress. Here are some sort of brief thoughts about how they're related to each other. The black hole comparisons, I think, suggest to me that we should be looking for solutions which involve some kind of inherent relationalism and also something potentially like retrocausal or teleological in character. I think the reference frame approach I've just described maybe kind of fits the bill for that. It's certainly inherently relational because in that picture, properties such as position and spin to which quantum states assign probabilities are by definition relational. So quantum states which describe those things must be relational too. And at least in a sort of effective sense, it's going to look retrocausal. In some sense, the sort of unified space-time in which we all live only comes into existence in a sort of retrospective way. So it's a funny kind of retrocausality, but it certainly does have a teleological or retrocausal character. So perhaps that's one way of kind of fleshing out those intuitions that we're looking for something inherently relational or something retrocausal or teleological. With that said, there are other inherently relational and retrocausal approaches which seem worth considering. As I said, I also am very interested in Kent's approach and the retrocausality there. There are other things in this vicinity to explore as well. So I think that is potentially a space that has been a bit underexplored in the conversation over Wigner's friend paradoxes, and I think it would be interesting to explore that further. So that is everything I had to say. It was quicker than I expected. So thank you for listening, and I guess I'd love to hear if you have thoughts or feedback or ideas about some of the things that I'm confused about.
Sure, yeah, thank you. Yeah, Emily, thanks for the seminar, for presenting these two projects. I think that we can all agree and see that it's how it is related to the Templeton
Great, I'm glad.
grant as well. So we have time for questions, at least from my side. It was a lot to digest. So if
very
you can
fast,
send
yeah.
it like the seminar, the slides
Yes,
afterwards,
yeah,
I'll be like greatly appreciated. So yeah, I always learn from your.
Yes, I will send the slides, but I do emphasize that this is work in progress, and so
yeah.
it may be like wrong, so don't disseminate it too much.
I don't mind. Absolutely. Yeah, thank you. Yeah, but we have time for questions, Matt.
Might be. I mean,
I'm volunteering you.
not a question so much as a comment. Something that I'm wondering about whether you can build something out of. So if presumably you can reconstruct all of the systems that went into the black hole from the Hawking radiation, you can reconstruct not only the qubit, but Alice as well. And if you believe, everybody who works on these things seems to believe that, if you're going to believe there's a paradox, you have to believe, okay, everything's unitary and deterministic all the time, right? So, I mean, do we have reason for believing if Alice goes into the black hole and then makes a measurement versus Alice is reconstructed outside the black hole and makes a measurement? Do we have any reason for believing that those results might have to be the same? Because then you're going to get basically a one-to-one mapping between the Wigner's friend and the black hole paradox. Because if you bring her back out of the black hole, then it doesn't really matter that she went in, and it's just the regular Wigner's friend paradox. See what I mean?
Yeah, I mean, I don't know if we do have a reason for thinking that those outcomes would be the same, because pure unitary quantum mechanics says nothing about the relationship between those outcomes. So you could very reasonably say that it's not going to be the same.
I mean, I think you can derive something about, if you are willing to assume something like local friendliness, I think you can derive something about it. So, for example, consider this is like a Shan-Gao type of paradox. So consider something like you have maximum entangled state, and this particle over here is measured. Okay, well, maybe this isn't quite the same thing. Okay, so scrap that. I have to think about this. There may be something you can say there.
I think certainly within a lot of these approaches, they don't like you making any claims about the relationship between observations made by different observers, and I'm not quite sure how that applies to the case where it's the same observer but also two different observers. But
well, I mean,
like figuring that out would be complicated.
So the resolution. One of the reasons why it's hard to do this Wigner's friend type of stuff with the kosher specker, as opposed to, I mean, I know there's some examples, but it's hard to do it compared to using like a Bell experiment, is precisely because if I do a sequence of measurements and then they're all undone unitarily, there's no reason for believing that if I start and end with two measurements that are compatible, that if I got this outcome down here, I have to get that down.
Well, exactly. Yeah.
But sometimes you can do stuff with like a local friendliness type of assumption where which ends up sort of basically implying that that has to be the case. So I'm wondering whether you can do something like that here.
What do you mean by a local friendliness assumption? You mean just assuming that there is an outcome? Or do you mean
So-
assuming that it can be communicated?
So, okay, here's an example, right? So this isn't a contextuality example, but just have an EPR state 0, 0 + 1, 1, right? And over here, measure in the computational basis, okay? So that has some outcome. Okay, now over here, measure in the computational basis, the outcome has to be the same. Have a super observer undo it and measure in the computational basis.
Yeah.
Right? The outcome still has to be the same because this outcome is still the same, right? So those two outcomes have to be the same.
Yeah.
Now a local friendliness assumption will tell you, yeah, but it doesn't actually matter. It shouldn't actually matter if this thing was measured or not. So from that you can infer that if I have a maximum entangled states and I measure in the computational basis, it's undone and I measure in the computational basis, the two results have to be the same, regardless of whether there was actually a measurement here or not.
I think in general, that kind of reasoning is only going to work if you assume third person universality, because if you assume first person universality, this result could be erased or something, and then you'd never be able to check whether it was the same.
Yeah, I have to think about that, but yeah.
Justin, can you do a favor and check if there is a question from the audience? If there is an audience, there, please.
Can you move the camera?
No, that was at the
okay.
beginning of the.
I guess not.
No questions on Zoom yet.
Yeah, no question. More questions here. Emily, can you elaborate just a little bit more? You said somewhere in your slides that if we ditch absolutely resolve observed events, that may cause or will cause some epistemically
Yes.
problems. Can you elaborate a little bit on that?
Yeah, well, I mean, in the Bong-et-al paradox, the absoluteness of observed events assumption is playing like two main roles. One is to assume that each observer gets just one outcome. So that's like to rule out the Everettian scenario. And the other is to assume that one outcome can be communicated to other observers in a sort of like accurate and reliable way that reflects what was really seen. So denying either of those, I think, leads to pretty severe epistemic problems. You know, the Everett interpretation has some well publicized problems to do with probability and how you can make sense of probabilities in that context. The other one involves basically denying that observers can communicate with each other and share their measurement outcomes. I don't think we can make sense of the practice of science if we do not believe that we can actually communicate with each other and share our information. So I think either of those results is going to lead you into a very bad place. So I think that what I proposed here, I think I'm trying to have a way in which this probability distribution could be indefinite or ill-defined in some sense, but we still have reliable communication and we still have only one outcome for our observer.
I mean, I think it is relevant to say that this, you know, as far as we know, this kind of situation where you would have, you know, you wouldn't effectively have absolute, it's only occurring in extreme scenarios.
No. Well, two things. One is that most people who have proposed this as a resolution have proposed the correct resolution is a general kind of relativism where observers just are never connected to each other. So that's pretty clearly going to be a more general problem, but also like the interaction that's taking place here, at least on the face of it, seems to be Alice and Bob just having a conversation about a measurement outcome. So in the case where Bob asks Alice, it seems like that's just an ordinary conversation. So if you don't get accurate communication there, it seems hard to see why that wouldn't apply to every case where people talk about measurement outcomes. So maybe there's a way to make it work, but I think you'll need to have like quite a clear principled way of explaining why this is a problem only here and doesn't then extend to every other conversation.
Sure. Yeah, but even if suppose that Matt and I were doing some measurement and then he did a measurement and that he's trying to communicate his outcome to me and I'm saying, oh, okay, so I'm not listening or whatever. So perhaps we disagree at this level, right? But we can reconcile our perspectives later on. Perhaps that's a possibility, right? Although I'm teaching off this possibility that we can agree on something, like literally on the matter of the fact of the matter of the thing, but perhaps we can like come up with a way to compatibilize our perspectives later on. So that.
Well, sure, but I mean, what would that be? Because I mean, if you're denying absoluteness of observed events in a sort of general way, that seems to imply that you can never succeed in communicating anything with Matt. Like you will always be stuck in your little world and Matt will be stuck in his little
That's
world
hard.
and no information.
Okay, so then it's way more.
It's
severe.
difficult for me to understand.
Yeah,
Thank you.
I think for sure, as Matt says,
Right,
if this
yeah.
just occurs like in this one case and at no other time, then fine.
Fine.
But
yeah,
the worry is that it seems like it's going to be more general in a way that's just going to undermine all of the sort of social practices we have in science.
Wait, more questions? No, so let's thank Emily again. And I think next week we have lined up Nadia Bernardes from Federal University of Pernambuco. If it's not Nadia, it's Fernando Brandão from Caltech, but I'll have to check. But it's either one.
One or the other.
Yeah. So thank you.